Okay, good morning, everyone. Thank you very much for joining the 101 stream. The session we are running this morning is an introduction to storage, and our speaker is Georgina McRae. Before I hand over to Georgina, just a couple of points. We would love to hear your questions. So there is a chat window, which you should see at the bottom of your screen. So if you have questions, please just put them in there, and we have some time at the end to go through those questions. You would also love to hear your feedback. So you see a QR code here on this slide, and you're able to give feedback via this QR code. And you will also find a link on the last slide that Georgina will show. And we are recording the session, so you're able to view the replay afterwards. So Georgina, over to you.
Thanks, Lena. Good morning, everyone. Thank you for joining my talk today. As Lena said, I'm Georgina McRae. I am a client technical specialist in the IBM Systems Storage Group. I joined IBM in January of this year, and over the months since then, I have been thinking through the question, what is storage, and finding my own answers to that. Now, what is storage is slightly different for open systems and for enterprise storage, and I'm really looking forward to sharing with you today what I've learned about enterprise storage. So, on to you, my virtual audience. Joining this talk today and spending your time to join GuideShare Europe, I see you as the future CIO of your company. You want to see the best technical thoughts in the field and see best ideas and share ideas with people that work in the same mainframe space. So whether you are completely new to mainframe and just sort of finding your feet with the different terminologies and different things about it, or whether you're a seasoned professional, it's relevant. This talk should be relevant to all of you because storage has an important place to play in your systems environment and in your enterprise environment. So, on to our objective. Our objective today is to build or refresh your knowledge of first principles of storage for mainframe. So I'm going to start that with a very simple idea. If I was storing an old Beach Boys CD in a cardboard box, then I would expect some things from the box in a sense, or when I put it in storage, it's out of sight and out of mind. And I want to know that when I then access that CD again, it's secure in the meantime. It hasn't been scratched, it hasn't been broken. I can get it out whenever I want and the quality of it won't have changed. It also needs to be accessible. Whenever I remember the CD, maybe in 5 years' time, I need to ideally know where it is and also be able to get it out when I want it. Now, part of both of those things is to do with reliability. I need to always be confident that it's there. No one's moved it, no one's changed it, nothing's happened to it. And finally, if I was then to move house and move my box with me, then I'd expect the data to be portable. It's not going to get damaged again, secure, accessible, none of that's going to change in the process of moving it somewhere else. And all of these different qualities matter to enterprise storage as well. But with enterprise storage, we are storing data. Now, data is the world's most valuable resource. This is quite an old cover of The Economist from 2017, and yet it remains true today. According to Forbes, the world is generating more than 2.5 quintillion bytes of data per day. Now, that sort of number is quite hard to picture and see at scale. So to explain that in a different way, 2.5 quintillion bytes of data is equivalent to every adult and every child, which is 7.5 billion people on our planet, each filling 8 32 gigabyte iPads every day, every single day. So data is the world's most valuable resource, but it is also at a huge scale. For today's talk, I would like you to join me in a role play. For the next 40 minutes or so, you are a data architect or a data engineer thinking through some questions. Firstly, what are the key considerations in our design of storage for mainframe? And then why does that need to be considered? And finally, how do we address those issues? Being an IBMer, I'm going to focus on the IBM's answers to how we address key issues. But for today's talk as an introduction to storage, I encourage you to focus on what and why throughout this presentation, because the same priorities apply to all storage solutions. And as future CIO, it's your job to evaluate the best features and system solutions for your environment. On to our brief for today. Our brief is to design storage to best complement the performance, the resiliency, and the security capabilities of the mainframe. Now, IBM Z systems make up about 80% of the mainframe marketplace, and they're the driving force behind lots of industries like financial industry, government industry, and insurance. Mainframes run 30 billion transactions per day and handle 87% of all credit card transactions. So no one can afford for their mainframe to stop. If a mainframe were to stop, then the business would stop. That brings us on to the first question of the day. What medium should we store our data on? Now, the answer to that depends on the data. In your system architecture, some processes need to be performed as quickly as possible. So your priority for that data is quick access and performance. But then if you're generating regulatory copies and backup and archive, which is also important to a system's, to your whole system, then your priorities are different, such as keeping it cheaply, and that is better suited to a different physical medium. So it's often better to use different types of data storage for different functions within one system. Now, the two types of media used in IBM storage for mainframe are flash drives and virtual tape drives, or tape drives as part of a virtual tape system. So to introduce them both, flash drives are electronic media designed for optimal power and reliability. Physical tape stores data sequentially on a tape that then is offline by design. By that, I mean that once you've loaded the data onto a tape, you can disconnect it from your system, put it in a box, take it somewhere else. And it being offline, firstly, makes it the cheapest form of storage per gigabyte, per amount of data. And secondly, there are security benefits, because when the data is offline, there is an air gap and no cyber attack can threaten something that is disconnected from the system. So to put that in the context of virtual tape, which is the solution we've got on the screen, virtual tape combines the performance of disk-based operations with the capacity and scalability of physical tape. What I mean by that is you can process up to 256 jobs at a time and optionally stacking to tape, again, if that function is for archive or backup or something where tape is best suited to it. So for time constraints today, in today's talk, I'm focusing on design principles for the all-flash solution. Now that is called the IBM DS8900F, and I may refer to it as the DS8K as well for the whole family of that type of system. And in the DS8900, the priority is helping the mainframe with the fast transfers of data for the billions of transactions mainframes process that we mentioned before. So we're on to our first design thinking principle. What can we do to optimize performance from our all-flash storage? So let's look at how we connect the storage to our mainframe. Why does that matter? According to Forbes, storage latency is the most critical factor when assessing the overall performance of virtually all transaction-based computing workloads. So, in that case, how can we address that? The IBM response for DB2 workloads is to create a direct physical link between the DS8K and the mainframe. Within 150 meters, Z hyperlink is a mainframe attached link that provides up to 10 times lower latency than high performance Vicon. It provides the fastest application response time in the market at 18 microseconds minimum response time. Now that's 5 times faster than its closest competitor, and any reduction in latency, and that being the best sort of option, helps any organization to accelerate their core transaction processes. So there are lots of other things we can do to consider performance and how to optimize performance. One I'd like to look at today, firstly, is explaining the move towards all-flash arrays. So on this slide, we've got lots of different trends in the all-flash array marketplace. But to, again, explain the move to all-flash, I'm going to first just talk a little bit about disk drives. Now, disk drives were, before flash, the sort of fastest and most powerful media. And the reason why flash, or the first reason it says on the screen, the reason why flash is becoming so popular and the choice for the DC900 is the need for speed, that performance and reliability are unmatched and that all flash is the best media for that. But also disk drives needed more heating and cooling than the all flash solution. And as well as that, disk drives take and require and use more electricity. So both of those things play into the green agenda, and you can minimize your environmental footprint by moving to all flash, while still prioritizing top performance and reliability. So now that we know we're using the media with the highest performance and reliability that we can, there are other considerations again. Now, one of those is maintenance. Now, to think about maintenance, I'm choosing a slightly strange analogy of a double-decker bus. Now, given that, at least if you're in England, then we're currently in lockdown, and with the whole sort of, we mustn't do unnecessary travel and things, it's a slightly strange thing to be thinking about. But the reason why I choose a double-decker bus is for the request stop buttons distributed throughout. Now, it's likely that some of those buttons, probably the ones at the front, maybe the ones near the doors, are going to be used more often, pressed more often than other buttons in that bus. And the more you use something, any electronic media, the more likely it is to fail from overuse. So again, the way we could optimize reliability in that way is if we could distribute the use of the buttons equally throughout the bus. And this applies to our storage question. So in flash drives, there are a range of capacities. There are high performance drives, which start at 800 gigabytes of capacity. And there are also high capacity flash drives that go all the way up in size to 15.36 terabytes. Now there are other sizes along the way, but the smallest is 800 gigabyte, the largest 15.36 terabytes. So if one of those drives, or one of your drives in your system, is getting more workload than others, then again, like the buttons on the bus, it may fail from overuse. And it is better if we can distribute all of the data evenly across the system. So let's ensure that that happens. Again, how IBM addressed this is a feature called Easy Tier. Now, Easy Tier enables automatic, intelligent data placement across flash tiers. The idea being that you promote hot data that you're using more often, and you could demote cold data to the appropriate tier. Now that works for a multi-tier environment. For example, if you had 2 different sizes of high capacity flash drive, then it could demote and promote accordingly. But in addition, if all of your flash media were exactly the same capacity, so that would mean you have a single tier environment, then it would still divide data equally across all of those drives. So the impact of that and of addressing uneven distribution of data is to bring greater availability to the system and greater performance. Now, what about cache? If we were in a room today and this weren't a virtual conference, then I would get a show of hands for those of you that really understand cache, and I would know from that whether or not to explain it. Because I can't do that, and for those of you that are beginners to the space and beginners to storage, I'm going to explain cache the best I can. Any of you on the call that really do understand it, if you could let me know any better analogies I can use, I'm always keen to learn. The way I'm going to explain it is going back to my CD. So that CD that I put in a box at the beginning of the presentation, if I was getting it from Flash Media, I'd be getting it out of my cardboard box, out of the case, putting it into the CD player, and then playing the track. If the CD were in cache, it would already be in the CD player, ready to play, the instant that I want it. So therefore, cache is the easy access and also temporary storage in your DS8900 or in your storage, whatever system that might be. So why does cache matter? Well, a better cache means better I/O response times and therefore higher performance for your system. If you can get more things through cache or more I/O going through your cache, then that means you have more I/O being easy access, accessed faster than others within your whole environment. So I'll leave a few seconds for you to think about this. How can we best optimize cache? Now, your first thought may be increase cache size. Now, that's true in the sense that if your cache is bigger, you should be able to put more I/O through it at any one time. What I'm going to explain with the diagram on the screen is that cache hit ratio can be at least as important as your overall cache size. Now, cache hit ratio is about space efficiency and using all of the space or as much of the space as possible that is available to you in your cache. So to explain this, we've got A, B, and C on the screen. Each one is the way that a company configures their cache. Now, A configures their cache in 32 kilobyte segments, and B configures it in 16 kilobyte segments, and C in 4 kilobyte segments. Now, in each of these tables, the total cache size is 256K. They are the same. So I'm going to explain this diagram with a cork block and the idea of chests of drawers. So for this analogy, this cork block is 4 kilobytes in size. Now, if I have 3 chests of drawers and the total chest size, again, is the same for each company, I've got bigger drawers and fewer of them in company A, where they're 32K size, and then medium-sized drawers and then really small drawers in company C. Now, the small drawers are 4K size, so that means if I'm putting this block, this I/O, as it were, this instruction, into a drawer, I fill the drawer. There's no space left. Whereas if I were to put this small I/O into a bigger drawer, then there would be empty, unfilled space within that drawer. The drawer would still be occupied because that's how cache works. The cache segments have a maximum of 1 I/O per segment, but the actual sort of total cache space would not be filled, even though every drawer would have something in it. So this goes back to a GSE talk you may have attended last week. In the Intro to ZOS talk, which was on the 5th of November, and the recording is available on the website, ZOS uses 4 kilobyte blocks as standard. So that means that this cork block is the smallest size I/O that could be coming through your system from the mainframe. Now, only IBM, which is company C, has engineered the granularity in cache to work best with these small I/O workloads. And that means when an I/O comes along that is of that small size, IBM doesn't waste cache space in getting it through. Now, to see that on the screen again, the sequence used on the screen is 4, 8, 16, 4, 8, 16, all the way up to 24 I/Os. Now, again, it being temporary fast access storage, you're getting these going through all the time. But again, the granularity means that you can fit the smaller I/Os in smaller spaces in that cache. So the sort of cache hit ratio that IBM can achieve is normally in the 90s, 90% of all the space available to you in your maximum cache. And so hopefully that explains how the cache hit ratio is at least as important as overall cache size to getting I/O through the system. There are other considerations for cache. Now, one is processing power. The more oomph you can push behind, for example, the speed of getting these in and out of your drawers of the chest of drawers, the more I/O can go through your cache, and therefore, again, the more powerful it is. Also, another answer you may have thought of to that question is algorithm, because if your cache can predict what you're going to need in it, then you don't have to take as long getting data in and then out of your cache. For example, back to my CD again, if the CD player were to know that I always play track 5 first, then it could preload that track and I wouldn't have to scroll through the other songs to get to it. So algorithms and processing power, as well as, again, cache size and cache hit ratio, are all things to consider as a data engineer when you're designing or thinking about the cache that you need or the cache that is the best for your system. Now, IBM use Power 9 processors for that. Again, all different companies will use different algorithms and approach it with different sort of processing power and size. So now we've addressed some performance points. Your storage system is primed to complement your mainframe really well. But what about security? Cyber attacks are no longer a question of if, but when. Cybersecurity Ventures predicts that there will be a ransomware attack on a business every 14 seconds by the end of 2019 and every 11 seconds by the end of 2021. For a sense of scale, Gemalto's breach level index, which is now part of Thales, estimated that 15 billion records have been compromised worldwide since 2013. So a simple and quite commonplace answer to the threat of cyber attacks is encryption. But returning to the breach level index, 4.5 billion records were compromised in the first 6 months of 2018, yet only 1% of those were encrypted. So this is surprisingly low, and it asks two new questions. Firstly, why don't businesses encrypt more of their data? Or why don't businesses encrypt all their data so that when data is breached, more of it would be encrypted and the people who have suddenly gained access to it can't use it? And again, with that question, how should we design encryption? So there are different reasons why businesses don't encrypt their data. One reason is that the traditional method of encryption, which is selective data encryption, is costly, it's resource intensive, and it forces a business to take a view about their attitudes towards risk. So that includes what parts of the data should be encrypted, where should encryption take place within your system, and who is responsible for encryption. So focusing on where encryption takes place, data can be in the clear before it reaches, for example, a switch in your system that will encrypt the data. At that point, before it gets to the switch, there is a security exposure or a chink in your armor, and at that point, your data is susceptible to attack. We should therefore design encryption to exist at rest, in flight, and in the cloud, so that you don't have chinks in your armor. Ideally, you would have every link as resilient as the rest. Now, again, to mention how IBM addresses this, IBM's encryption is 100% AES 256-bit encryption, and it meets or exceeds NIST encryption standards for data in flight and at rest. Now, IBM solutions are designed with the IBM Z in mind, so that encryption works across the mainframe, the DS8900, and the tape system, the TS7770, that I mentioned at the start. So it is worth thinking about those standards and worth thinking about the levels of compliance and whether you have chinks in your armor in the way that different companies or software products address encryption for your enterprise system. Now, other reasons why businesses don't encrypt their data include because it could have an impact on performance. The actual process of encrypting data within your system takes power away from other processes going on, or because it is difficult or can be difficult to manage access. If you don't have the encryption key, you can't unencrypt your data. So who's going to have that key? How many keys are there going to be? How is the life cycle of the key going to work? All that sort of thing. Now, IBM addresses those questions by making encryption hardware-based at host level with no application changes. That ensures that encryption has near to zero impact on performance. But again, there are other ways you may approach that issue, and there are also various ways to simplify and optimize encryption key management that data engineers consider. Now, if I were going to address all of those today, I could probably fill the hour with looking at just the different approaches to encryption, the different things IBM does to do that, the different ways you can think about encryption keys. But for today's talk, we're returning to this image on the left, the World Economic Forum's Global Risk Report. And as you can see, natural disasters, extreme weather events, and impacts of climate change all come higher in likelihood and impact than cyber attacks. So even though the scale and the implications of cyber attack are very large on business, there are even greater risks to your system. So thinking about that then, what can we do about hardware failure? Now, hardware failure can be as simple as you're updating something and it goes a bit wrong, the software's being updated, there's maintenance, or just unplanned downtime for a few seconds. So why does that matter? We've mentioned right from the beginning how mainframes can't afford to stop. If your storage stops, you suddenly lose access to your most valuable resource, your data. So you need to ensure that that will never happen, or you need to do everything you can in your power as a CIO so that that can never happen to your system and you never lose access to your data. So again, a question for you, how can we ward against hardware failure? Now, the simplest answer to that is have more than one copy. And there are many ways, again, that storage addresses that and answers that, that desire. So if you have two copies, ideally, you'd like them to be fully identical. Every single data point in one is copied in the other. So if you lose access to one, you have exactly the same complete set of your data still available to you. Now, the terminology by which, or the technique by which that replication takes place is called synchronous replication. Now, to explain synchronous replication, we're going to imagine for a minute that I am the primary DS8900 and I'm linked to the mainframe, maybe with the Z hyperlink, maybe with FICON, but I'm attached to the mainframe and I'm receiving all the data points. Now, you, my audience, you are the remote DS8900. So I get the number 1 from the mainframe and I send it across to you. Now in synchronous replication, I wait for you to say 1 in order for me to know that you've received that number. And when I know you've received it, I then tell the mainframe, and the mainframe tells me the next number in the sequence. So that guarantees data consistency. It means that I will only send you the next number and have the next number when I know you've received it. And it's all done very quickly as a cache-to-cache transfer, but it means that, again, ideally, you have two identical copies. If anything were to happen to me as the primary DS8900, you have all of the data points that I had. So, considering different ways to configure that, the first thought of having two copies is have them in the same room. If you do testing on one, then the other one is still available in case that testing maybe means that one system is slightly isn't fully accessible. But if there's a hardware subsystem failure, suddenly you've lost access to both copies again. So there clearly isn't enough to ward against risk. So let's move them one step further apart and put two DS8900s. So we're having two, again, physical systems, both of which have that synchronous replication in different buildings in the same site. So this is definitely an improvement. It means if there's maybe, again, a localized hardware failure in one, the other one is still online and you still got access to it. And you should, again, have an identical copy through synchronous replication. But back to all the problems that face us. Let's go back to the global disasters or natural disasters. Maybe there's a flood. And if they're both in the same site, the flood is very likely going to affect both of these DS8900s and take both your copies offline. So we've still got an issue that they're too close together to be secure against risk, against extreme weather, or even just against a power cut. So let's move them even further apart. Now, synchronous replication works up to 300 kilometers, meaning that you could have your two different DS8900s 300 kilometers apart, and you could still benefit from the synchronous replication and try and get that identical copy. So if one goes offline for a power cut, the other one keeps going. Now, metro region is part of the metropolitan distance of 300 kilometers, and IBM calls this type of replication for these three configurations metro mirror. So metro mirror is great for that identical copy having two copies of the data, but unfortunately, you could have a flood affecting the mainframe, the DS88K on the left, and then you could have a power cut affecting the other. So even though you've put them 300 kilometers apart, having two copies does not protect you against all possible failures and all possible issues. And we're back to exactly the same question. What can we do to further protect ourselves against global disasters? So there are two ways to answer that. The first is have more than two copies of your data, add more copies. And the second is increase the distance between your copies. Now, data travels at speed, but the further it has to travel, the longer it will take. Up to 300 kilometers, synchronous replication works well. But beyond that distance, there is a substantial lag in data transfer that makes synchronous replication impractical. And it's impractical because it would require the primary DS8900 to work at a lower speed, waiting for all of the different data points to come back or to be confirmed as read by the remote copy. Another issue, if you have more than two different production sites or more than one, then if they're both sending data to a remote copy, there might be a different lag from those two systems, and it's quite difficult or brings its own set of issues in trying to get that data sent to the remote site in the right order. So how do we mirror data between volume pairs in a storage system, so between two different DS8900s, over a distance greater than 300 kilometers without having an impact on overall performance? Enter asynchronous replication. Send the I/O to the remote site in increments, which allows the DS8900 and the mainframe to perform at their best and the remote copy to continue to build in the background. Now, the reason why you need this is that if you didn't have asynchronous replication, as I said, the DS8900 would slow down to wait for that replication to take place. But another issue is that the mainframe waits for those processes to keep going at everything it can do at its very top high level with the millions of data points it processes. So if the mainframe sees a lag in the data being copied through a remote copy, it would take that offline. It would say this application is not responding, off. So asynchronous replication allows those two machines, the DS8900, your primary DS8900 and your mainframe, to work as optimally as they always do. And then it allows the remote copy to be built as well as it can be in the background without affecting that performance. So the way that IBM terms this when it's beyond that 300 kilometer distance and when you start using asynchronous replication is global mirror. We've now added two different further configurations to the three that we had before. One is having two sites at global distance, and the other is that you can have three sites, or uniquely to IBM, you can have four sites. And that then benefits from putting the metro mirror and the global mirror benefits together. So a little bit more on global mirror. Now, as I've said, there are different issues with trying to get a remote copy to be as complete a set of data as possible. And IBM addresses that with different features, but all companies would address building a remote copy in a different way, because you have the same questions. As a data architect, it's how do you make that copy as reliable as possible and as complete as possible, given the global distance you're working at. So just to mention them by name, you've got flash copy operations at the remote site with Global Mirror, and global copy operations, which work between the local and the remote to copy out of sync tracks. So there are other things to sort of check that that copy is being built correctly. And a further thing is that you can define the time intervals at which these different processes take place. So in terms of your overall system, it depends on sorts of maybe the size of workload that you're using or the different things about your remote copy. Now, there are two final storage terms for me to explain to you today. When there's a blip in data transfer between two subsystems, there is an impact on business continuity. If I resume my role as the primary DS8900 and you resume your role as my remote copy, so the DS8900 that's far away, I'm going to try and give you the sequence 1, 3, 4, 2, 5. Now, for this analogy, we're returning to synchronous replication. So I say 1, I wait to hear you say it back to me, then I say 3, and so on. But a disaster hits. My Zoom connection fails for a second, and you haven't heard any number beyond 3. So now we have an RPO and an RTO, a recovery point objective and a recovery time objective. So the recovery point is the point that we can both recover to where we know our data is consistent. So we both had the numbers 1, 3. I may have had more numbers than that when it went offline, but you didn't hear more than 1, 3. So our consistent recovery point is after those two data points. Now the RPO, the recovery point objective, is how much data we can afford to lose without an impact to business continuity. So hopefully the fact we've both lost, effectively the system's lost the 425, won't affect the business continuity for us. Now, the recovery time objective is the amount of time taken to recover from that number 3 and resume data replication from before. So the system being back online, I then tell you the number 4, hear it back, then I tell you the number 2, and then get to the end of that sequence. Again, recovery time objective is the objective at which, the amount of time you can take to recover without serious business implications. So in an ideal situation, we would like the RPO to be 0, and we would like the RTO to be as short as possible in order to minimize any impact of downtime. So both RPO and RTO are important considerations or things to be aware of when designing your system. For example, they may impact the frequency of copies and backups that you need to generate, because if you have a backup at all these different increments, then regardless of how big the disaster is and the recovery point, you still have backups up to that point. So it can help with that sort of protection and planning. So finally, we have two examples of using synchronous metro mirror with asynchronous global mirror together. Now, this one on the screen, we've got metro mirror in a single location and global mirror at long distance. So we're combining the different configurations we've just looked at, the different configurations for metro mirror with this global mirror benefit. Now, we can also have a 3-site replication. In this, we've got a metro mirror to a local intermediate and then the global mirror distance. Again, I think I mentioned before, IBM can uniquely offer 4-site replication as well. So this is 4 hardware copies across different DS8900s. You might have your primary and then 2 different sites with metro mirror up to, let's say, 300 kilometers away in different directions, and then your remote copy halfway across the world. And that should mean that, well, every time you add a new copy, you're resilient to sort of a further disaster in one of those, and it would still mean you have access to your data. Now, we can add details of RTO and RPO to these configurations. Now we have addressed what they are. RPO depends on bandwidth, it depends on distance, and it depends on user specification. So it will be lower if you are not using the 300 kilometer distance, but maybe a 100 kilometer distance, for example. Now that can be as low as 0 with metro mirror, meaning that you may lose 0 data points, absolutely no data, if there's little recovery, if there's suddenly a disaster strikes, because all of the synchronous replication has perfectly copied every data point up to that. The recovery point objective can be as low as 2 to 5 seconds to the remote site with global mirror, if both metro distance copies failed at the same time. Now, the recovery time objective is designed to be less than a minute. So taking RPO and RTO into account enables you to better plan for your mainframe storage requirements. And those requirements, as you said right from the start, are to keep your data secure, reliable, and accessible, and to optimize performance. Now, I've included this slide in the deck for your own reference. You can download the deck from the GSE website, and if you want to compare things between the two different ways you can have the DS8900, then this slide's there for you. The only thing I'll point out from it is the system memory, because that is the cache. So when I said what about cache, again, cache size matters, but cache hit ratio matters, and all that sort of thing. So you can put the numbers on here into context of the different features we've addressed today. So in summary from today, we've covered storage decisions that will help you to keep your data secure, accessible, and reliable. And that takes us to the end of your introduction to storage. And thank you for listening. We're joined today by Alan Nash, who is the IBM Enterprise Storage Product Manager for UK and Ireland. And we're both here to answer any questions you may have.
Thank you very much, Georgina. So far, I've not seen any questions in the chat, but everyone, feel free to post them there now. And Georgina and Alan can go through them then.
Yeah, concur with those points. Thank you very much. Very informative, an excellent presentation and presenter on such a technical matter. Bravo.
Okay, thank you very much, Georgina. I haven't seen any questions in the chat yet. I don't know if you wanna hang out a bit here to just see if questions are coming up. Yeah, you're getting very good feedback.
Yeah.
Thank you, everyone. Thanks.
Okay, so just a quick reminder, we are running a 101 networking session tomorrow afternoon from 4 p.m. until 5 p.m. It would be great to see a lot of you on that session. So I think we have some trivia quiz planned, and yeah, just try to run the session for everyone to get to know each other. So it'd be nice to see you there, and you will find that session also in the agenda. Then just one quick reminder, it would be great to get your feedback. So on that slide that Georgina has open right now, you see the link and the QR code. So I'm sure Georgina would also appreciate your feedback on her session. And you can find the slides and the recording on the GSE website. With that, I will go ahead and close the session if there are no other points. All right, then thank you again for joining. Thank you very much, Georgina, for that great session, and enjoy the rest of your days.
Thank you.
Cheers, Robert.